Hi, I'm Hirna from HORYZN.
And I am Szilard from WARR, and together we are competing for the European Rover Challenge. Our joint team consists of two student initiatives from the Technical University of Munich.
Hi, my name is Leonard and I'm the software lead of Project Creator. I'm Bastian and I'm the mechanical lead.
I am Szilard, the project lead, and together we build our rover, Felicia. As mentioned earlier, the development of the rover is taken care by WARR Space Robotics. The team is structured to three divisions, to the mechanical, the electrical, and the software team. Each of these teams focuses on solving its respective set of challenges. The development of the drone is taken care by HORYZN. They dedicated one part of their team to build the drone, Phobos. And why do we want to participate in the ERC?
Because participating in the ERC for me means challenging myself by applying the skills and knowledge I've learned in university and by building the rover.
The ERC creates a competitive environment that motivates me, and we also like to see cool projects of other teams.
And we want to stress test the rover, and we can't wait to do it on a real Mars yard.
Our rover Felicia was designed with a focus on reliability and maneuverability. We use 4 independently steerable wheels, which ensures a very capable navigation system and allows for maneuvers such as spot turning and grabbing. This, in combination with our purposely designed wheel profiles, allow for excellent navigation in challenging terrains. Further improving our navigation abilities, Felicia utilizes a rocker suspension. The rockers are differentially linked, which ensures sufficient ground contact at all times. All in all, our drive system has been proven to allow precise and reliable navigation.
In the electronics team, we are doing both hardware and firmware development. For the hardware, we are developing our own custom-made PCBs, and for the firmware, we are writing our own code. The power coming from the battery is being distributed by our power board. For the electrical side of the drive system, we are using off-the-shelf driver boards from Trinamic. To ensure safety, we implemented a PCB that protects against reverse polarity, overvoltage, and overcurrent. To also protect against back EMF of the motors, a 2.3 mF capacitor bank was added to the circuit board.
The rover uses 4 sensors for odometry measurement. 1 RGBD camera facing forward, 1 facing backward, a LiDAR facing the ground, and an IMU. All 4 odometry sources are fused using an extended Kalman filter to provide the rover with a final combined odometry estimation. Additionally, the LiDAR is scanning the terrain in front of the rover and incrementally building a cost map where cell cost increases with terrain steepness. This gives rugged and highly inclined areas high cost, which will prevent the rover from trying to traverse them, instead making the rover search a path around them. We are simulating the Mars yard with the Aruco tag landmarks placed according to the coordinates that you provide to us. When the rover sees at least 3 landmarks, it triangulates its location to correct odometry errors using point-and-plane solver algorithms from the Open Computer Vision library. When the rover receives a goal, it computes a path to it using the A-star algorithm. It then proceeds to autonomously navigate that path, paying attention to the local cost map computed from the LiDAR scan to assess whether the terrain in front of the rover is traversable.
The rover can show its ability to drive forward, backwards, and because each wheel has a steering motor, it is possible to do a spot turn. It also can drive uphill And, in case of an emergency, all power is cut as the emergency button is pressed.
We use a coaxial quadcopter made out of glass fiber reinforced plastic. The platform includes an optical flow for indoor navigation, a down-facing camera for attack detection, and a onboard computer and Wi-Fi link for remote access.
Our drone can move upwards, forwards, backwards, to the left, to the right, it can also rotate and land manually. A safety system was implemented in such a way that pushing a button on the controller initiates auto landing.
Unfortunately, we ran into some delays concerning our robotic manipulator. Therefore, the best we can show you is this excerpt from our multi-body dynamic simulation. We use a 6 degree of freedom arm with a total reach of approximately 1.2 meters. Our links are made of trusses using carbon fiber tubes and aluminum gusset plates. Where possible, we use slip rings to allow for infinite rotation, especially in axis 1, 4 and 6. What we can show you is our version of a robotic gripper. It functions based off a rack and pinion gearing system, and jaws made of foaming TPU, which allows them to deform around our target objects and improves our lifting capabilities. In this clip, you can also see our current storage system for both rock and surface samples. It uses a single-point load cell for accurate weight measurements. Storage containers are mounted on linear rails, which allows for easy and quick removal of the samples. Our gripper jaws are interchangeable and will be adapted for the task at hand. Our deep sampling system remains unchanged from last year's ERC due to insufficient manpower and time constraints. The drill system uses 2 lead screws for a coupled vertical motion of both the drill itself and its housing relative to the rover. For the drilling itself, we use a specialized auger which allows for taking deep samples at specified depths.
Thank you very much for watching our video. We all hope to see you soon in Krakow. And now, let's do some stress testing.